Assalamu alaikum. How you doing, guys? This is the third recording in the series, and we're going to talk about the design of tension reinforced rectangular beams. Okay, and we're going to tackle the T-beams in a separate recording. Now, remember in the previous, I think the first recording, we mentioned that in one of the assumptions, I'm going to use the actual stress distribution or a simplification thereof. And the question is, why would I need a simplification? Well, if you look at this 3D representation of this cross-section right here, you can see the actual stress distribution. Now, imagine if that wasn't a rectangle, if it was a circle, for instance, or some other shape, then you can see that this becomes a little bit more complicated. Add to it if I have, let's say, compressive reinforcement, or I have an axial load, then using this shape will actually complicate things a little further. So what I want to do, I want to come up with something simple, easy to handle, and that gives me the same answers. So we're going to introduce to you what we call Whitney's block. What he did, he said, how about if I represent this distribution right here by a rectangular distribution? Because the area of a rectangle is quite easy. It's the width times its height. Now, I'm keeping the width be the same. So this is still b. This is still b. Here I'm introducing a new variable, which I'm going to call a. And what this one does, it's actually moved up from the neutral axis. Okay. C is still the location to my neutral axis. Where here's my neutral axis, I'm still keeping the tension as the area of steel times the stress in the steel. So this kind of showed me the 3D representation of that. Okay, now looking at this 2D distribution, the goal is, again, I want to match my compressive force with the location of the compressive force. I want them to be at the same location because I do not want to have any difference in the calculated internal moment. So what I know that this C right here must equal to this C over here. The location here must be the same as the location here. So here I'm going to introduce this value, which is gamma, and which is an unknown value to me. And I'm going to say this is equal to gamma f prime c. Remember here we had it as alpha f prime c. Okay, so now this is my gamma f prime c. This is A that we talked about, and obviously the location is at A over 2. So from that, by the way, I know that A over 2 must equal to beta C. Now, A is still an unknown, okay? But I know that A is some fraction of C. So here I'm going to introduce a new coefficient, which is equal to beta 1. So I'm simply saying that the value of A is simply beta 1 times C. Okay, so with this, I'm going to try and figure out what the new value of gamma is and what the value of beta 1 is. Now, C here is equal to alpha f prime c, c times b, which must be equal to gamma f prime c, a phi b. So this area here must be equal to that. Plain and simple. Okay, now the b obviously and f prime c will cancel each other out. From that, I'm able to find gamma, and gamma is simply alpha times c over a, but I do know what c is, so I'm going to replace that with a over beta 1, which now will cancel this unknown a from here, and from that I have the value of gamma is equal to alpha over beta 1. So since I know alpha, if I figure out what beta 1 is, I can actually find out what gamma is. So for me to do that, I will go back to the fact that a over 2 is equal to beta c. Okay, now I'm going to remove c and put a over beta 1. So from that now notice that a will cancel out with a, which will lead that beta 1 is equal to 2 beta. So if I go in here and replace beta 1 with 2 beta, I'm going to have gamma equal alpha over 2 beta. I know what alpha is. I know what beta is, right? So I can easily figure out what the values for gamma and beta 1 are. So I'm just setting up this small table for the values that we know so far. Here is my alpha, here is my beta. We know if this is less than 28 and this is 0.72, this is 0.425, and we know if that's larger than 55, it's 0.56 and 0.325. I did calculate some in-between values at 34, 41, and 48 to get some values for alpha and beta. Now, we know that beta 1 is equal to 2 beta. From that, I've noticed when this is less than 28, I'm getting 0.85, 0.8, 0.75, 0.7, and 0.65. This is telling me that beta 1, again, is in the range between 0.65 and 0.85. It can never be larger than 0.85 and can never be smaller than 0.65. What is interesting, though, is the value of gamma. Now, gamma is alpha divided by beta 1, which we already figured out from here. So as you can see, it's 0.85, 0.85, 0.85. For higher value, it's becoming 0.86 and 0.86, which is not much of a difference. So from that, I'm going to make gamma constant, and that is going to be equal to 0.85. So from that, now, the compressive force is going to be 0.85 times F prime C times A times B. Okay, remember, this is supposed to be my gamma, which I now figured out. And it's going to be constant. So it's going to be 0.85 F prime C A times B. Again, this is valid. Circular cross-section, presence of reinforcement, T-beams. If you have a triangular section, it's valid. Okay? Now, A is equal to beta 1 times C. Now, beta 1 is going to be equal to 0.85 minus 0.05 F prime C minus 28 over 7. Again, beta 1 is confined between 0.85 and 0.65. So it can never be more than that, and it can never be less than that. Okay? So that's how we calculate the compressive force. So we were able successfully to transform this complex shape into a simple rectangle. Now, how do I make use of that? Now I'm going to calculate my moment, obviously, which I want. Then from that, simply my moment is area of steel times Fy, when I'm assuming yielding, obviously, times D minus A over 2. Again, here's where I'm getting that from. Here's my A, beta 1 times C. Here's my 0.85 F prime C. And again, this is A over 2, this location, and this here is the distance D. So that moment arm between this compressive force, which is this distance right here, is simply D minus A over 2. Now, how do I find the value of A? Simply compression is equal to tension. This being area of steel times Fy, and this being the 0.85 F prime C B times C A, and from that I can find the value for A. Again, introducing ρ as area of steel divided by BD, then my moment is going, and I'm using this moment equation right here. Again, replacing area of steel with raw BD, and replacing the A with this guy over here. So as you've noticed, I'm getting the same exact equation as we did before. And again, it's going to be 0.588, but I'm using 0.59. There are some books like to use what I call the flexure resisting factor, and they call that R, and then my nominal moment is going to be RBD square, and there are some tables which kind of link R with B and D in the moment. I usually don't like to use that, especially with the aid of calculators, computers, Excel spreadsheets, and all that. So I'm simply going to use this equation right here. Okay. Now, I have to look at the row balance distribution, right? So again, we said row balance was the ratio at which crushing and yielding happens at the same time. This will not influence the definition of my C, by the way. Still going to be epsilon ultimate divided by epsilon ultimate plus epsilon y times D, regardless of whether I used Whitney's block or the actual distribution. That's not going to change. Now here I'm going to use the same equation. Again, compression is equal to tension. This now being the tension force, and this is now equal the compressive force. And again, raw balance or raw FYB times D is equal to 0.85 F prime C A times B. It used to be C and now it's A. And I know there's a relation again between A and C. So replacing that over here, notice I got the same, well, almost the same, because this is now 0.85 instead of alpha. So it's going to be 0.85 beta 1 F prime C over Fy epsilon ultimate divided by epsilon ultimate plus epsilon yield. And the ultimate stress again is 0.003, and this is again 0.002. So this is again my balance reinforcement ratio. So let's use an example to use Whitney's block. So again, he wants me to find the nominal moment at which this beam will fail. Again, I'm using the same exact beam, 600 millimeters for D, 250 millimeters for B. I'm having 3 phi 25 as my main reinforcement, and these values did not change. So I'm going to use the same thing. I'm going to calculate raw, and found that to be, well, we already found that out. Now I'm going to calculate the neural balance, which is 0.85 times beta 1 times F prime C, and if you notice, it's almost the same. And that's, since my raw is less than raw balance, it will fail due to yielding of steel. Well, the new thing is I'm now going to calculate A, which is area of steel Fy divided by 0.85 F prime C times B. From that, I can calculate the nominal moment, which is the area of steel, times the yielding, times D minus A over 2, and I got almost the same value. And you can also see that C is also the same. Okay, so this is again using Whitney's block, and I will end the example right here. So you will notice I always talked about yielding, and for me to ensure yielding, I would like to use what we call an under-reinforced beam, and we always need to emphasize that my raw should be less than raw balance. Why? Again, I do not want to reach the compressive strain limit of concrete, because crushing of concrete is a brittle failure, it's a sudden failure, and I do not want that. Material properties are not known precisely, as we said before, and that was one of the main reasons why we did that ultimate strength and that probability distribution and multiplying that by the reduction factors. Strain hardening of reinforcement steel not accounted for. There is some strain hardening after reach the yield point, but that I'm keeping that an added benefit to me. Well, it's not one added benefit because it actually adds to the strength of the steel. Again, I want to be below the yield. Actual steel area provided will always be larger than required. And as I said at the beginning, when we talk about the actual diameter of my steel bars, if I say like 525, it's more than that. It's like 25.4, 25.3, depending on the manufacturer. And it obviously gets larger with higher diameters. Okay, so that's telling me that my area of steel is more, and I want it to be less. So that's why I want to have surely to be less than my raw balance ratio. And the extra ductility, as I said, provide increased deflection capability substantially, which means I can actually watch my beam as it deflects, which will give me ample time either A, to clear the building, or do some maintenance and fix the beam if I can. So how does that translate to the code? So the code says, I'm going to give you safety limits. I'm going to have those safety limits defined by two things. The first one is what I call the strength reduction factor. And the other one is I'm going to ask you for a minimum tensile reinforcement steel, which I'm going to call epsilon T. That strain, I'm going to give a limit for you. Okay? So let's talk about the first one. So the first one is if I have a structural element in which I have a moment and an axial force, or a combination thereof, then my phi, which is the multiplier, is going to change between 0.65 to 0.9. Okay? If I have only shear force to account for, then this multiplier phi is going to be 0.75. If I have torsion, it's going to be the same value. If I have bearings, it's going to be 0.65. Okay? And we'll talk more. So this is what I'm dealing with. Okay, here is the range. So if I look at this table right here, you can see I have what I call a net tensile strain, epsilon t. I have a classification. Now I have two types of transverse reinforcement. And by that I mean the ties or stirrups. Okay? And we get into that with much detail when we start talking about shear design. So for now, I want you to know that I have spiral type and what we call other types. Okay, if it's a spiral, then my phi is going to be equal to 0.75. If it's other, it's going to be 0.65. If my net tensile strain is larger than epsilon ty plus 0.003, then I will call this a tension controlled member. Okay, and for that the phi is going to be equal to 0.9 regardless of the type of lateral reinforcement I'm using. Okay, now if my epsilon ty, and we will be dealing mostly with this, with a tension controlled section, again because flexure is a tension controlled section. If my epsilon t, the net strain that I'm going to calculate, is less than my yield strain, then I have what I call a compression controlled, and that's going to change between 0.75 for spiral and 0.65 if it is not. Then I have what I call a transition. The transition is when my strain in the steel is between the yield and between epsilon ty plus 0.003, then my phi is going to be calculated according to this equation. If it is spiral lateral ties or stirrups, or if it's other than a spiral, it's going to be 0.65 plus 0.25. So what you will notice, if I put my epsilon t equal to ty, you will get 0.75 here, and you will get 0.65 over here. If you put it as epsilon ty plus 0.003, then you're going to get 0.9 and 0.9. So this table is kind of summarized in this figure over here. So if my epsilon t, and I'm going to show you how we're going to calculate it in the examples because we can calculate it. If it is less than my yield strain, which is 0.002 for grade 60, then I'm in the compression region member. If it's in between, and if my epsilon t, which is equal to epsilon ty plus 0.003, so again, if I'm using a grade steel 60 or 420 megapascals, then this value here is going to be equal to 0.005. So if I'm between 0.002 and 0.005, I call this a transition between compression controlled and tension controlled. On the other hand, if my epsilon t is larger than 0.005, then I'm at what I call the contention control zone, and my phi is always equal to 0.9, and I will be thriving to get that. Now, for deformed reinforcement, epsilon ty is equal to fy divided by ES. So if I have, let's say, a yield of 550 megapascals, then it will be 550 divided by 210 gigapascals, and that should be your epsilon ty for that grade. Now he says for grade 420 reinforcement, it shall be permitted to take epsilon ty equal to 0.002. Okay, and we're going to use that tremendously. All right. Now, you will find in some other references where they do not want to calculate the epsilon t. Well, in fact, what they do is they calculate c and divide that by dt. Let me just show you what I mean by dt. So if this is my cross section right here, and this is my reinforcement, and let's say I only have one layer, okay, then again to the center we call that d. And now, since this is only one layer, and this is the furthest reinforcement from my compression fiber, then this is also equal to dt. So in this case, d is equal to dt. On the other hand, if I have another cross section in which, let's say, I have two layers of reinforcement, okay, then the value of my d again is to the center of the reinforcement, which is going to be between these two layers, and then this is the value of d. The definition of dt again is to the reinforcement furthest from the compression fiber. So now this here is from the center to the last layer. I'm going to call that dt. So this is the dt that I'm referring to right here. Okay. So if I have Fy 420 megapascal or grade 60, then the C over dt value is going to be equal to 0.375. And if it is epsilon 0.002, then it's going to be 0.6. So if I want tension controlled, the C over dt should be less than that. If I want it to be compression controlled, it should be more than 0.6. You will find I rarely use this. I actually calculate the net tensile strain directly to figure out what the value of my phi should be. Okay, so again, both limits are controlled by the net tensile strain epsilon t of the reinforcement farthest, to emphasize, from the compression face of the concrete at depth dt. So if I go to the definition of rho balance, which we found, okay, so I'm going to get the same equation, but instead of using the epsilon y equaling to 0.002, I'm going to replace that with this, which is my actual epsilon ty plus 0.003. Okay, because he's telling me I don't want this to be less than that. Okay, so I've controlled this. So now this I'm going to call my rho max. So my maximum reinforcement ratio is going to be 0.85 beta 1 f prime c divided by f1, because and epsilon times epsilon ultimate divided by epsilon ultimate plus fy plus 0.003. Okay, so again, this is the epsilon ty plus 0.003. This is to ensure that my phi is going to be equal to 0.9, and this is going to ensure that I'm having a ductile failure and that it is less than rho balance. So the new code requires me, the ACI code requires me to use this as my maximum balanced ratio. And I will show that in an example, and hopefully that will make things easy. Now, other things that we need to know what we call a concrete protection for reinforcement. What we are mostly interested in would be not exposed to weather or in contact with ground for slabs, joists, and walls. So if it's less than 536, then I'm going to use 20 millimeter as my cover. For beams, columns, and pedestal and tension ties, then it's going to be 40. For foundation, by the way, it's going to be 75 millimeters. So this is the amount of cover that I'm going to put under my tie. So other things that I need to worry about, D is usually 2 to 3B, or what we call B web. B web actually stems when I have a T section, and this is my B web. So you will always you see in the code referring them to B web instead of B, because for rectangular cross section, B is equal to B web. Here I'm talking about the spacing of reinforcement, which is between the bars, which is essential to me, especially in sizing. So for parallel non-precessed reinforcement in horizontal layer, clear spacing shall be at least the greatest of 25 millimeters diameter of the bar, or 4/3 the largest diameter aggregate in the concrete mix. So if I have a cross section right here and I'm placing, let's say, 2, 3 bars, then this distance here between these two bars, this is the horizontal distance that he's talking about. So this should be the larger of 25, or diameter of the bar, or 4/3 diameter of aggregate. So if I have 525 reinforcement, so this distance then should be 25. If it's a 530, then this distance should be 30. If it's a 518, then it should be 25, because that's the minimum. If I have maximum aggregate, let's say 1 inch, then the distance should be 4 3 times 1 inch, which is 4/3 the 25, which is going to be larger than the 25 millimeters. So this is the horizontal spacing, and we're going to talk about the maximum spacing down the road as well. So this is now the minimum. So I'm not going to, I don't want you to worry about the maximum spacing, just worry about the minimum spacing for now, which is one of those three. Okay. Now, if we have more than one layer, so if I'm going to add another layer over here, then this distance between these two is a minimum of 25. So it really doesn't matter if you have a larger diameter of the bars. The only thing that is a minimum 25. So you could either use 25 if it makes you feel happy. You could also put the distance of the larger diameter if you will. But again, the least is 25 millimeters. So even for phi 30, you still can use 25 millimeters. Now for longitudinal reinforcement in columns, pedestals, and truss, you can see that this distance now, instead of 25, is now 40 millimeters. Instead of diameter of the bar, it's now 1.5, but they still kept the 4/3 of diameter of the aggregate. So what does that mean to me? That means to me, I can find out what my minimum B is, which is the minimum B that will contain all the reinforcement. So you will find out during the design, I'll show that in an example, that if you do the design, you need a certain B, but when you put the reinforcement, you will see that they will not fit. So for you to figure out what that minimum B is going to be, it's going to be equal to the number of bars, right? So if I have, let's say, 4, 5, 25. Let's do this right here. Okay, so let's say I have here 4, 4, 5, 25. Okay, then the minimum B obviously is going to be, they have to contain all these 4, right? Plus the distance between them, right? The spacing. Now the spacing here in this case, since this is a phi 25, so this is going to be also equal to 25. And since I have 4 diameter, which means I'm going to have 3 spacings. This is 1, this is 2, and this is the third. So this would be 4 times 25 plus 3 times 25. Now, the cover, we said for beams, is going to be 40 millimeters. And that's going to be this distance right here. Actually, let me draw. Oh, no, it's right. Let me draw the stirrup right here. So this is the distance of my 40. It's going to be this way, and you're also going to have 40 under the stirrup as well, plus 2 phi stirrups. So if this is, let's say, phi 10, then you're going to have 1 stirrup here and the other one right there. So the minimum B would be 4 times 25, which I guess this comes to 100. Add to it 75. And then we have 40 plus 10, 50. So this is 10. So this is going to be 2 times 50, 100 as well. So the minimum B that I need, or the minimum width that I need, is going to be 275 for me to be able to contain 4 phi 25 in that cross section. Okay. So in this drawing right here, again, here's my 40 millimeters minimum. Again, it's a minimum, so if you want to use more, you can. This is my phi 10. Since this is 3 phi 32, then again, this is 40 millimeters plus half of that, which is 16, plus 10, which is 26. Hence, I get the value of 65. So the cover is always to the beginning of the stirrup. So this is my cover. This is my 40 millimeters cover. Okay. Again, the spacing S is the minimum of 25, phi of the bar, or 4/3 of the diameter of the aggregate. Again, if I want to figure out what my D is, it's going to be simply H, the whole value, minus the cover, which in my case here is 40 millimeters, plus phi stirrup, which is 10, plus 1/2 the bar, which is 16 in this case. So this is how we figure out D. As I said, we usually know what D is, so I usually would like to find out what my H is. So H would be simply D plus this parentheses up here. Okay? So for this case, for instance, my H would be equal to D plus, here my cover is 40, plus my phi is 10, plus my main reinforcement is 25, so it's going to be 12.5. Okay? So that's some practical things that we need to worry about. And I'm going to show that in the following examples. So here, this example, what is the nominal flexural strength and what is the maximum moment that the cross-section can handle according to the ACI code? So this is an analysis type of a problem. I'm giving you all the dimensions, I'm giving you everything. All you have to do is find what that moment value is. So for me, I'm using B is equal to 300. I'm using D equal 450 millimeters. I have 4 phi 25, and F prime C is 28, and Fy is equal to 400 Newton per millimeter square. I did not give you any information about the stirrup because I already have my D, so I probably will not need it here. Now, for area of steel of 4 phi 25, this is equal to 963.5 millimeters square. From that, I can calculate the reinforcement ratio, which is equal to area of steel divided by B times D, and that's 0.014544. Here, I just did not want to confuse you, but since the ACI code has been only a year out, so you might find out some people are still using the old definition of rho max. And the old definition of rho max, they use the epsilon T is equal to 0.004. So if you find that in some books right now, because not all of the textbooks has updated itself to the new rho max, but this is the rho that I'm not going to be using at all. Okay, so I will not be using this. But I thought I would just show it to you so that you don't get confused. And I also want you to show you the difference between the rho max and the new rho max. Okay, so if I calculate the new rho max, and that's the only example where I'm going to refer this as to new. Okay, after that, rho max is this. Okay, it's the rho max that I'm giving you at the beginning. So by using that now, it's going to be 0.85 F prime C over Fy. Again, this is now, since I'm using an Fy of 420, so that I always remind you this is equal to epsilon Ty plus 0.003. And we set for grade 60 or Fy 420, I'm allowed to use it as 0.002 plus 0.003, and that value will be 0.005. And by the way, we used to call that in all designs as rho 0.005. So again, this is my rho max now, right? So again, you've noticed that the rho max now is less than what it used to be before. So now the emphasis now is in using less steel than before, okay? Now if you compare that to the rho balance, now the old one was 0.714 and the new one is now 0.62. So I'm using 62.5% of my rho balance value. Back in the days, our reference, we did not use rho max, we just used rho balance, and we usually, our designs were about 75% of rho balance. So you can see how over the years, the ratio to rho balance has decreased further and further, emphasizing the use of less reinforcement. Okay, now here I'm saying that rho is less than rho max, which means it's failure by tensile yielding. Now, what you have to understand, it's not because it is, well, because rho max essentially is less than rho balance, okay? So if my rho is less than rho max, obviously I'm going to be less than rho balance, obviously I'm going to fail in yielding. Now, you might find in some old designs where this is not the case. So if you're doing your design, let's say a new design, you always have to emphasize that my rho is always going to be less than rho max. That's your goal, that's your target. Now, you might find previous designs. You might find them like 3 or 5 years ago. If you want to do some checking, you want to add, a story, you're going to do something to that some of your old buildings, then you will find that some of these designs in which row is larger than row max, or might be even larger than row balance. Okay, then at that point you have to deal with it. So at that point you have to calculate Fs the way that we did before, and you can use the same equation for C because that's not going to change. So you find C from that equation that we developed before, and then simply your A is just going to be beta 1 times C. So you're going to find out what that moment, or what that moment is going to be. So moving forward in your designs, always make sure that your row is less than row max. Okay. If you find some old design where this is not the case, it doesn't mean that everything is bad, but it means that you have to come up with different calculations. Because you're going to find some old building, somebody would say, hey, I have a 3-story building, I would like to add another floor to it, and then you have to do some recalculations, okay, to see if the new beam or the old beams kind of sustain or will be able to handle the added 2 or 3 floors even, right? So now rho again is less than rho max, which is less than rho balance, so I'm going to have failure by yielding. So from that I can use all the equations that I had before. A is now equal to, again, this is area of steel times Fy. Again, if it's not yielding, you have to find out what this Fs is. Divide that by 0.85 times 28 times 300. This is now A. Then my nominal moment is 963.5 area of steel of 4525 times 420 times 450 minus A over 2, and this is the nominal moment. So again, this is the nominal moment, and that's not the design moment. To find out what the design moment is, I have to calculate epsilon t. Okay, so now C I can find out from A over beta 1, and that's equal to 115.5 divided by 0.85, which is equal to 135.88. Okay, so from that, epsilon t now is equal to epsilon ultimate dt minus C over C. Since I have only one layer of steel, then simply dt here is equal to d. Okay, so from that, I'm able to find what my epsilon t is. You will notice that it is more than 0.005. Again, you will find some references or some textbook like to use the C over dt value. So if you calculate that, it's going to be 0.302, which is less than 0.375, which again will give me a value of phi equal to 0.9. So now my design moment. So if I'm posting a moment, I'm saying, hey, how much this beam can handle, I will tell you this beam can handle up to 290 kilonewton millimeters. Okay. 200 kilonewton, no, that's meters, sorry. So it's going to be 291 kilonewton meter. Okay. So that's how we design. So if we found the nominal moment, multiply it by the reduction factor, and that's now my design moment. All right, so this is how much this cross-section can. There's one thing also you should keep in mind. You will find instances where you actually don't need any reinforcement. The moment might be either small, the cross-section is too big. That depends on some factors. That depends if it's part of a continuous beam. As you know, when you have a continuous beam, you usually develop your cross-section based on the maximum moment. Okay, so you might have one section where you have a big moment, it will require a bigger cross-section, but when you go to the other span, or the third span, for instance, you will see that you have smaller moment, and you will figure out that this cross-section by itself can handle this moment without reinforcement. But again, according to the code, we always have to add some reinforcement, and that reinforcement, we call it A as minimum. So we always must have some reinforcement. And that's going to be equal either 0.25 square root f prime c over fy times b web times d, or 1.4 b web d divided by fy. So for this example, I calculated what I called rho minimum. Again, I divided that just by bd. So you can see it's missing here, and then d also is missing from there. So you can find that this is 0.0031 and this is 0.003. So I take the larger of them, and the larger is 0.003, which is less than the row that I already provided. So I am on the safe side. here. The fourth recording of this is just going to be pure examples. Okay, so you guys stay safe, have a nice day, and we see you.